So today we're going to go back and review a little bit on continuity and differentiability, and I'm going to use 4 very specific parent functions to do this. All right, so the first one I wanted to look at was f of x equals 1 over x, which I've already graphed here. Okay, and remember, we did ask you that you were to make yourselves responsible for knowing the graphs of these parent functions. And that's for many reasons, not just to be able to graph them, but also to understand their behaviors. Okay, so we know that this function has a vertical asymptote at x equals 0. And that's because right here, the domain is that x cannot be 0. And that's a non-removable discontinuity. Okay, so we have a vertical asymptote at x equals 0. We know that this expression can never be equal to 0. So we also have a horizontal asymptote at y equals 0. So I'm just going to go ahead and label a couple of things or sort of define a few things here. The first one is going to be the domain of this function. I'm actually going to come down. Okay. So the domain of this function is all x values such that x is not equal to 0, right? Because we can't divide by 0. In interval notation, that would be all negative values for x or all positive values for x. And here I've not included 0, but I should be able to get very, very close to 0. So that's why I've got the exclusive parenthesis here. Okay. Then I look at the graph of the function and I realize for continuity that the function is actually continuous over its own domain. And so the function is also continuous from negative infinity all the way to 0, right? But not including 0. And then again, from values very, very close to 0 all the way towards positive infinity. So this function is also continuous on its own domain, so negative infinity to 0 and 0 to infinity. And then we want to talk differentiability. Okay, and so just a reminder, differentiability means I can take the derivative of a function on the intervals for which the function is continuous, but also smooth. Okay, so the word smooth means nice, right? Transitions of tangent lines. Okay, nothing sharp. Okay, like corners and cusps. All right, so we're looking for the intervals on which the function is both smooth and continuous. And I look at this and I realize that it's smooth and continuous again on its own domain. So the function is also differentiable on the same set of intervals. And we're just going to go ahead and verify that by looking at the derivative itself of this function, okay, and the continuity or the domain of the derivative. So I'm going to go ahead and rewrite my function. Instead of saying 1 over x, I'll say x to the negative first. And then I'll just use a general power rule to take the derivative of that. And I get negative x to the negative second, or negative 1 over x squared. And then I look at the domain of my derivative. And I notice that, again, the only thing that's true here is that x cannot be equal to 0. I can't divide by 0. So the domain of my derivative is the same as the intervals of differentiability for the original function, right? Differentiable on means the derivative exists on, okay? So I know that this function is continuous and differentiable on all negative real numbers and all positive real numbers, but just not at 0. Okay. The next one we're going to look at is the square root function. Okay. And here I see that the domain of the square root function, this one's pretty easy, I think, for most of us, is going to be everything from 0 to infinity. Remember, we can never include infinity because that doesn't give us an existential value. But the function exists at 0 because the square root of 0 is in fact 0. So the domain of this function is all non-negative numbers, so 0 and positive numbers. All right, and then we have continuity, and continuity again would be from 0 to infinity. And if you want to include 0 in that continuity, you would just make sure that you say, you know, from the left, right? You're talking about continuity from a direction, right? Some people would argue that 0 is not included, but to be consistent with the way our textbook is defining intervals of continuity, we will include the endpoint because we can start the graph here and then continue onward to the right. Okay. Now, where is the function smooth and continuous? Now, this one might be a little tricky because is a function smooth at an endpoint? Not necessarily. So instead of jumping into differentiability, let's go ahead and take the derivative of our function. We should first rewrite it as x to the 1/2 power. And using the general power rule, we'll have 1/2 x to the negative 1/2 power, which we can rewrite as 1/2x to the positive 1/2 power, or 1/2 times the square root of x. Okay. And then we look at our denominator and we see that we have an x in the denominator. So we know that x cannot be 0, but we also know that x cannot be a negative number because we're taking an even root of x. So this is a situation where x must be strictly positive. Okay. So the domain of our derivative here is that x must be strictly positive, so not including 0, because if x was equal to 0, we would be dividing by 0. So the domain of the derivative, okay, is the interval of differentiability on the original function. Oh, I spelled that wrong. All right, so it is the interval of differentiability on the original function, and it is the domain of the derivative of that function. So this function is differentiable everywhere from 0 to infinity, but not at 0. Not differentiable at 0. Okay. All right, next one, we're going to look at the natural log of x. All right, so now the domain of the natural log of x. We know we've got a vertical asymptote at x equals 0, that we are going to approach that value. So we know that we have values from 0 to infinity. Again, we cannot get to an existential number when we're talking about infinity. And then also, we're never going to quite make it to the y-axis, so we will not include 0 there. We can only take the natural log of strictly positive numbers. All right, continuity here is easy as well because this is a smooth curve. Nice and easy to draw, no holds, no asymptotes after x equals 0. So the continuity interval is the same as its domain. All right, now it would be a good idea for us to go ahead and take the derivative of the natural log of x. Oops, didn't mean to do that. Okay, so taking the derivative of the natural log of x will give us f prime of x equals 1/x. Now we have to be careful here because if x couldn't be negative to begin with, it can't be negative now. All right, we can't just all of a sudden allow negative numbers. Okay, so we know that x is still going to be strictly positive, and then the only thing that comes about here is that x cannot be 0. So we're going to go ahead and say we can't have x equals 0 because that's 1/0, which is undefined. So x cannot be 0, but x was always strictly positive from the original function. We can't all of a sudden bring in negative numbers. Okay, it's not going to work. So the domain of my derivative is technically negative infinity to 0 and then 0 to infinity. But I'm going to cross something out here, so just be patient. That's saying that I can take the derivative of this function, right? Here's the function. I can take the derivative over here. Well, no, because there's no function over here. So we're going to ignore this interval from the domain of our derivative because I can't take the derivative of a function that doesn't exist here, okay? So this thing is only differentiable from 0 to infinity. Okay. All right, and then the last one I have is the absolute value function. Okay, now, this one's a little tricky on the derivative because we've only really touched on it maybe once or twice. And that was back when we were using the limit definition of the derivative. So I'll go ahead and give you the derivative formula for this. But I will encourage you to go back and look at the limit definition of the derivative to make sure you understand where that comes from. All right, but really quick, this domain for this function, you can take the absolute value of anything, right? So the domain for this guy is actually all real numbers. And for that matter, again, a function is continuous over its own domain, as long as there are no issues. And if you look at it, you can keep drawing without your pen leaving the paper, right? So this thing is continuous from negative infinity to infinity as well. Okay. But we do have a problem with differentiability. If I take the derivative of my function, I get x over the absolute value of x. And way back in the beginning of unit 1, right, we talked about the limit definition of the derivative. We talked about limits of functions that look like this, all right? And we realized that there is some discontinuity in this function, okay? So as I look at the derivative here, it's x over the absolute value of x. I know that the domain of this thing is all real numbers except for, I can't divide by 0. So the domain here is all real numbers except for 0. Which means this function is not differentiable at 0. This function is only differentiable for strictly positive numbers and strictly negative numbers, but not 0. And let's talk about why when we look at the graph. This point at x equals 0 is what we call a corner. The function is not smooth and continuous. It is continuous, but it is not smooth at x equals 0. So because it's not smooth, it's not differentiable at 0. So it's going to be very important that we understand differentiability and what that means for each type of function as we go through the next part of the course.